Okay, welcome back. This is the 2009 May Unit 1 AS Physics paper. We're looking at Section B in this video. There was a previous one in Section A and the 1 mark questions that you get when you get 10 questions. And we're going to have a look at this one now. It says explain the difference between a scalar and a vector quantity. So there you get 1 mark if you say that a scalar has only a magnitude and a vector has both a magnitude and a direction. In the second one, which is slightly more interesting, we're asked to answer a 3-mark question, which is quite tricky to get the 3 marks. Okay, I've been looking at the mark scheme and most people get 2 marks here. And the guy says, when asked to run 1 complete lap around a track, a student says that however fast I run, my average velocity for the lap will be 0. So you have to comment on his statement. For 3 marks, you have to think about the vector quality of the word he uses. He uses velocity, so we have to look at that. And an answer that I came up with here was to mention I made 3 points, 1 for each mark, corresponding to what the mark scheme asks for, and the 3 points are the velocity. You have to state the velocity is a vector. And after a whole lap, his total displacement vector is 0 because he starts here and he goes all the way back to the beginning. So if you do a vector from the start to where he ends, the displacement vector is 0. Even if the magnitude of the total distance has a finite value, the displacement is 0. So that's 1 mark to say that. Then you have to state in the second point that since the velocity vector equation is equal to the displacement vector divided by the time, and his displacement vector is 0, it doesn't matter what you divide it by. 0 divided by any number is also going to be 0. So that's the second mark, to realize that if you're dividing a number that is 0, which is the displacement by the time, that's going to be 0. And then the third mark is the one that most students don't get. And here I'm going to pull up the mark scheme so that you can see that I'm basing this statement on what they're saying. Student said, the particular student who answered this question said that he is referring to the fact that his total displacement will be equal to 0, so however fast he went, 0 divided by any number still equals 0. So his statement is true and accurate. The examiner awarded him 2 marks out of the 3, and he says here why. It says he identified the 0 displacement and how it leads to 0 velocity, but has not explicitly, and this is the key word here, stated why this statement that 0 divided by any number why is it relevant, e.g. by stating the formula for velocity. So he didn't include the formula which I included here, which makes the relevant statement related to its equation. And you need to link what you're saying to that, so it doesn't matter what his speed is, i.e. it doesn't matter the value of the time, right, which is related to his speed. It doesn't matter how fast he does it, how quickly or how small or large the time is. The answer is still going to be 0, and that comes out from the combination of using the equation and making the link to what he said, which 0 divided by any number is also 0. So those would be your 3 points, and most people there would miss out on 1. And this kind of analysis is very helpful it applies to other exam questions too. So let's have a look at the next question. Says in the game of pool sticks, sticks are dropped into a river from one side of a bridge and see which one reaches the other side first. It says a stick is dropped into the center of the river at A1, which is over here, and moves at a steady speed to A2, winning the game. Another stick is dropped into the river near its edge at B1 and ends up swirling around at B2. Add to the diagram to show that the water show the water flow at A2 and at B2. And I wish I could draw on top of this, but this is not an editable PDF. But the idea, hopefully you can gather from this already, is that it's talking about laminar flow and turbulent flow, since it's talking about swirling around at B2. So swirling should it should trigger in your mind the ideas of turbulent flow, and so the diagram around B1 should have something like this. This is question 12. Should have something like this, randomly swirling, in both directions, water, right? And this is what's going to happen to his stick, and that's why he's going to lose a lot of time in there, because there's no laminar flow. What does the laminar flow look like? Well, instead of having eddies like that, laminar flow should have flow of water like this, with parallel streamlines, indicating that there is very little sort of random motion there, and that the stick would move along those lines, and therefore travel a larger distance in the same amount of time. So that would be for the flow at A2 and B2. It says name and describe the type of flow at A2 and B2, and a lot of people have trouble describing laminar flow and turbulent flow. So I'm going to pull up the examiner scheme and see what they say here. There are the diagrams of the turbulent flow and the laminar flow. He's missing, they're not particularly good diagrams, so the critique of the examiner is probably going to be that they're a bit strange. But I would say that they need to be a little bit more sort of in several directions. That looks too regular to me, and turbulent flow is more random than that. And here he needs several lines to score the full marks. Now let's see his description. He says laminar flow is linear parallel flow, and turbulent flow is not uniform. Okay. So, the examiner says that this response shows eddies to gain 1 mark for the diagram, but a single line is not sufficient to demonstrate laminar flow, like we just said. So the examiner was generous with the eddies and the turbulent flow, but not with the laminar flow. Then he says the flow types are identified correctly with a spelling error, but not uniform is an insufficient description for turbulent flow, and I agree with that. Since parallel must involve 2 lines, this candidate just gained this description mark. Okay, so if we did the descriptions properly, we would have to say that turbulent flow, you need to say that there is in turbulent flow, there is the velocities, or you can say it even more technically, you can say the velocity vector of the water or of the fluid is changing at any point in the river, and is unpredictable. Okay, well, the laminar flow, that would get you the mark for sure, and then the laminar flow has parallel streamlines showing uniform velocity vector for the fluid. Velocity vector for the fluid at any given point. Okay, that's laminar flow. So hopefully those answers are more full and useful for you to use in the future. Let's have a look at the next question. Explain the meaning of the terms brittle and ductile, and sketch stress-strain graphs and use them to illustrate your answer. So that's a very good question for revision. Let's have a look at what we can write here. The meanings of brittle and ductile. Brittle ductile. And just before doing this, there's another point that you can make here that is very handy. You can use also when you, if it asks for one mark more or something like that. You can also say about turbulent flow that there is mixing of layers. Mixing of the layers. Okay, and here you can say that there, in laminar flow, you can say that there is no mixing of layers or of streamlines. Okay, but it's really layers of water that you're talking about there. Okay, so hopefully that's an extra mark that you can add onto there also. So let's have a look at brittle and ductile. Okay, so this is an interesting question because we need to be careful with our words here. So brittle, you need 2 marks for each. It's 4 marks the total for the question for all of them, but we're going to try to fill this up with everything that we know in order to be able to answer a question in the future, even if they asked us for like 3 or 4 marks for each one. So what's happening with brittle? Brittle indicates that a material can withstand a very small amount of plastic deformation. That's probably one of the best definitions of brittle deformation. Okay, that's one thing that's important. It can't. It's nearly the opposite of ductile in that sense that it cannot take a lot of plastic deformation. It also doesn't have. It also has a pretty straight relationship between the stress and the strain. So if you had a stress-strain graph, this is normally stress, and here you had strain. The graph is usually going to be a straight line, and then it's going to stop, or it's going to bend a little bit and then quickly break. The graph would get you the other mark, and then you can also state an example. So an example of a brittle material would be ceramics, just to show them that you know what you're talking about. That could also help. And so pretty much that's it for brittle. For ductile, we have to state the opposite, so that it can take a large amount of plastic deformation. It can accept or withstand, probably a better word there, withstand a large plastic deformation, but especially in the sense that more specifically that it can be drawn into wires. It can be drawn into wires. Okay, that's a really important one. And also when you draw the graph, you'll notice the other characteristic which you can bring, you can use words to qualify, which is that the graph would look something like this, and then something like that would happen. So the stress-strain graph, it gets to a point where you get a large stress or a small strain, right? Between here and there you get a lot of, the opposite, you get a long strain for a very small amount of stress, so you don't increase the force very much anymore, but it gets a large strain, so it stretches very much. And that's very useful if you want to make wires. And finally, an example would be copper, right? You look around, you see lots of copper wires, so you can use that as an example. Right, so let's look at the answers that they have. They have 2 answers, one of them by a candidate that didn't score so highly, and then one which scores highly. And it's interesting to notice how much attention the examiner pays to the words that are used and the details for the graph. The first answer says that if a material is brittle, it means that it cannot take much deformation. So, okay, so that's true. It's a bit vague. You see, it doesn't say plastic, it just says deformation. This is the graph shows it can take stress to an extent, but not very much strain. Okay, so that seems more or less fine, but it does give you the impression of a little bit of vagueness in terms of the key words. And then the second one says ductile materials are those that can be drawn into wires. A bit brief, and then the diagram. So let's see what the examiner says about this first. It says the response has satisfactory graphs, even though the linear region in the second graph is very small, so it should be straight for a long, just here it should be straight for a longer time and then bend over. But he says that it's probably due to the absence of a ruler, so interesting that they write this down. It says it gets the explanation mark for ductile by virtue of can be drawn into wires, so that gave him the mark for this one. But for the first one he wasn't so lucky, even though this was briefer, it was more specific. For the first one it says the explanation for brittle here refers to deformation rather than plastic deformation, so it wasn't specific enough, and uses the vague cannot take. This response would obtain the mark with the addition of a few words to say that it cannot take much plastic deformation before breaking. So the guy lost the explanation mark there, even though he wrote twice as much here as here. He lost the mark in the explanation because he was vague. So even though the idea is there, they haven't given them the mark. So they gave him the graph mark but not the other one. So notice that it's important we choose our words carefully and we make sure we think about them before we write them down. Let's have a look at the second guy and what he wrote and why he did a bit better. It says, brittle is a material that has a constant gradient on a stress against strain graph. A brittle material is one that fails shortly after its elastic limit and undergoes no plastic deformation. An example would be ceramics. Here's his graph, and that explanation is very good. Fails shortly after the elastic limit and undergoes no plastic deformation. So he's got a point there that I didn't make myself, that the material fails shortly after its elastic limit. In the second one he says it is the ability of a material to be drawn into wires, so that's his mark right there, and continues to say that it has a large region of plastic deformation on a stress strain graph. I don't know what that's beyond a ductile material yield point there are large increases in strain for minimal increases in stress, and that I mentioned too. And here's his graph with enough sufficient of a straight section, and then the behavior of the material changes when it gets above the yield point. So as an example would be copper wire, so he gives an example there, and the examiner is very happy with that, and he says that the response is very comprehensive and includes more than one mark-worthy explanation for both brittle and ductile. So he went over the top the student here, and he gave more marks than he actually even needed. Okay, let's go to the next question. It says, give an example of a ductile material and a situation where its ductile behavior is desirable. And this is hopefully common sense, but I'm going to have a look at what they wrote here just in case. It says, can barely read this, so for all my students with bad handwriting, be careful. It says copper can be hammered, I think it says there, into wires, although it's actually pulled, but I don't know what that says, into wires through which electricity is supplied. Aluminium can be molded into sheets. It says, this response correctly identifies copper, but does not gain the second mark because hammering into shape is a description of malleable. That's true. Hammering is to do with malleable rather than ductile, even though many ductile materials are also malleable. So a good example here, just to state, is this is 13b. A good example for malleable, just for general knowledge, is lead. Lead is malleable. You can make it into sheets if you want, but it's not brittle. But it's not ductile because it's brittle if you try to stretch it. So it's malleable, but it's not ductile. And on the other hand, copper is both. So many materials are both. Okay, hopefully that's handy information. Now, what is important there? They should have said copper, and then they should have said that it can be drawn into wires. Okay, so the verb there, the verb is drawn into wires. So copper, which is used for electronic wires to carry currents, and it can be drawn, not hammered, you hammer things that are ductile, but if you're going to pull things into wires, they are drawn into wires. Okay, it's a funny word. It's same as drawing, but it's a good word there to be able to use. Okay, let's look at the next question. The graph shows how the displacement varies with time for an object which starts from rest with constant acceleration. So constant acceleration, this is a distance time graph, that's why it's not a straight line, otherwise it would be a straight line if it was a velocity time graph for a constant acceleration. So this must be curving, and the gradient, in other words, the way that the gradient is changing must be at a constant rate, because it says that it's an acceleration that is constant. The question says, use the distance time graph to determine the speed of the object at time 4 seconds. So that should be easy enough. You draw a point here at the 4 seconds, and you says use the graph. So you're supposed to draw a long line there, a long triangle, and then find the gradient of that line, and that should give you the 3 marks, including the units. If you write down meters per second and you give an appropriate number of significant figures, which on this question, since all the information is given to 2 significant figures here, 25. It's the maximum accuracy, your answer should be also to 2 significant figures. Calculate the acceleration. So you just calculated the speed at that point, and now the acceleration, for me, would be to look at the graph and say, well, I just calculated the velocity at 4 seconds, and I know that his velocity initially here, the gradient is 0, so he must have increased his velocity by the difference between those 2 velocities in that amount of time. So I take this velocity, I subtract 0 from it, so that's just going to be that velocity divided by the time of 4 seconds, and I get the acceleration. Again, if I use appropriate units and significant figures, I should get my 2 marks for that question. Let's have a look at the next. Well, actually, I think this video is getting a bit long now, so I'm going to jump to the next video for question 15, and hopefully that's been useful for exam technique and a bit of knowledge too. See you in the next video.